the yes. Well, hopefully I don't spill any water on the laptop, and I don't have a clicker. Does anyone else? Oh, thank you.
Sorry.
Yes, unfortunately, I don't have hand-drawn slides today. I mean, I was just so impressed with that talk, both the content of it and also the means of delivery. It's just like, wow. So I've just got traditional keynote slides. So this is my talk on microservices. And I'm really going to cover three main themes. So the first one is I'm going to define what I mean by the microservice architecture, and I'm going to describe it as an architectural style, and along the way explain what an architectural style is. And I'm going to describe how the microservice architecture enables continuous delivery of complex applications. You know, that's a really kind of key thing, is that the microservice architecture is all about tackling complexity, and it actually has not so much to do with high scale. And then I'm going to finish up by talking about why microservices really are not a silver bullet, and they actually come with a lot of complexity and a lot of complex design decisions that you have to make. And I'm going to describe a pattern language that can help you use the microservice language, microservice architecture more effectively. So those are the main topics in the talk. A little bit about me. So I live in San Francisco. And I must say, I actually really appreciate the weather in Sydney right now. It's just cool, kind of like San Francisco weather. So I feel pretty much at home. It makes a change from where I was in China, where it was like 100 degrees and incredibly humid. I got my start in programming back in the mid to late 80s building Lisp systems. So Lisp, of course, being one of those AI languages, functional, then object-oriented. Ended up building compilers, garbage collectors, all the way up the stack to IDEs. Eventually, I ended up programming in Java, and my book, Pojos in Action, came out 10 years ago. So that was all about building applications with Spring and Hibernate. And it's sort of great to see that the Spring framework is still 13, 14 years later, it's still innovating, which is really cool. And then I ended up tinkering around with this obscure service known as Amazon EC2, which I am back when Amazon was best known for selling books. And that evolved into a Cloud Foundry, the original one, which was then acquired by SpringSource and then VMware, and then we were ejected out into Pivotal. So I was sort of part of that for a number of years. And the name Cloud Foundry, although not my technology, still lives on. So these days I do everything around microservices, consulting and training, kind of globally these days. I also have a startup. We're building a platform to simplify the development of business applications that are built using the microservice architecture. And I'm working on a book, which actually tomorrow or today, depending on how you look at it, US time, was going to be the Manning deal of the day. But if you tweet, you can get I'm going to have a raffle for a free copy, and then there's also a discount code as well. MICPAT OCD, apparently. So anyway, here's the agenda. I'm going to talk a little bit about what we mean by software architecture. We sort of throw this term architecture around a lot without really defining it. So I'm going to sort of talk about some 20-year-old concepts around software architecture, then dig into the microservice architecture, compare it with the monolithic architecture, and then talk about the pattern language and how that can help you apply the microservice architecture much more effectively. Okay, so what is software architecture? There's even conferences about that where usually it's like, hey, I'm from some internet company, and here's my latest super cool architecture that can handle millions of transactions per second and all that. And that's kind of at the level of the discussion that we tend to have. But if you go back and look at some classic definitions of what we mean by software architecture, it's a set of structures that you need to reason about a system. We're building a software system, and we need to kind of make decisions and, well, just plain think about it. And it turns out that architecture is a bunch of software elements and relations or relationships, and those software elements have properties, which can actually just be as simple as names, like kind of actually the name of a class, name of a service, etc. So anyway, so that's sort of the classic definition. It's a bunch of software elements and relationships and properties, which you can state more concisely as this triple, right? Elements, relations, and properties. But another way of looking at it is that it's just a bunch of boxes and lines, right, that architects draw in sort of PowerPoint decks and so on. So that's sort of kind of a fairly abstract definition. But if you think about it with a real-world analogy, you take the architecture of this building, right? In order to properly describe it, you need to look at it from different perspectives, right? There's the structural aspect to the building, the steel and the concrete. There's also the electrical aspect, all the wiring and so on, plumbing, heating, other sort of air conditioning, those other aspects of the building. So in order to actually properly describe its architecture, you need multiple blueprints, right, from different, from the perspective of different people, structural engineers, electrical engineers, and so on. So different stakeholders. And software is exactly the same. In order to describe the architecture of a software system, you need to look at it from different perspectives. And which another way of putting it is different views. And each view, in fact, is a collection of elements with relationships and properties. So we're back to that triple again. But to make it more concrete, there's a very classic view model, the 4+1 view model of software, which was first described by a guy whose last name I can't pronounce, Philippe, back in 1995. So his way of describing architecture is as a set of 4 views: logical, implementation, process, and deployment. And then there's the +1 that are the scenarios. So that's his 4+1 view model. Turns out it's an incredibly effective way to describe and communicate the architecture of a software system. So the logical view, and that sort of describes what we as developers create. So since we're programming in an object-oriented language, it's classes and packages. And then the relations between them are things like inheritance, association, dependency, and so on. So that's the logical view. That's what we create. And then there's the implementation view, where the elements are modules, as in jar files. And then there are components, which are collections of modules, which are the executables, the war files, or I suppose the ear files, or the executable jar files. Once again, the dependencies are, kind of like is composed of and depends upon. So that's the output of like our build tools, right? So we go from the logical view to the implementation view, which is our executables. And it turns out that the microservice architecture is actually a particular way of structuring the implementation view. So there is actually a reason for explaining all this stuff. And then there's the process view, which are the components from the implementation view at runtime. So a single war file or a single executable jar file at runtime will be a collection of processes, like a collection of Tomcats or a collection of JVMs and so on. And then the relations between those are the inter-process communication, REST or messaging or whatever protocol your application is using. And then finally, you have the deployment view, which are the machines that the processes from the process view are running on. And so those are 4 really useful views. And if you're creating architecture documentation, it really helps to structure it in this way. Believe me, I've seen so many of these architecture diagrams where it's like there's a bunch of boxes and I have absolutely no idea what I'm looking at. So these views are a well-defined kind of visual notation. And then there are the scenarios. So those show how for a given request, the elements of a particular view collaborate to fulfill that request. And that could be classes collaborating, it could be components, or it could be processes, or it could be machines. So for each of your views, you have a collection of scenarios that just sort of bring them to life. So that's the 4+1 view. So then the other concept is an architectural style. This is another classic definition, and it talks about a vocabulary of components and connectors. It's sort of different people, so they use slightly different terminology, but it's really elements and relations. And it's just basically imposing the constraints on the sort of palette of components and relationships that you can have and how they can fit together. Classic example of an architectural style is layers, right? Where it says that you have to organize your components or your software elements into a set of layers. Each layer must have a well-defined set of responsibilities. And then there are severe constraints on the dependencies between those layers. If you have relaxed layering, it can depend on a layer, can depend on any of the layers below it. Whereas if you have strict layering, it has to depend on the layer immediately below it. So that's a classic example of an architectural style. It gives you a set of elements and relations that you can compose your architecture from, and you have to obey a set of rules when you do it. Very analogous to building architecture, right? If you go look around at sort of Victorian or Greek or Roman, there's sort of a certain palette of sort of design elements that those buildings are constructed from that makes them Victorian or Greek or Roman. Okay, so that's architecture, architectural style, and it's like, well, who cares about this, right? Why does it matter? And what's really interesting is I think over the years, we've sort of kind of been building applications with a single architecture, 3-layer kind of, presentation layer, business tier, data tier, and it's all sort of been in the context of enterprise Java. And this architecture thing has sort of faded into the background somewhat, but we're building more complex systems, and in particular with the microservice architecture, you start having to think about architecture in a much more explicit way. So if you think about the requirements for an application, you can split them into 2 categories. There are the functional requirements, sort of what it does, the use cases and the stories that it implements. And those you can implement using any architecture you want, even a big ball of mud. It might not be pleasant, but you can actually do it. But there's the second set of requirements, the non-functional requirements or software quality attributes or the ilities, and which are things like reliability, scalability, sort of performance. That's not an ility. That doesn't end in ility. But in order to achieve those, you have to take into account the architecture. So that's the critical thing, is you have to pick the architecture that satisfies your non-functional requirements. And there's actually a long list of non-functional requirements or ilities. If you go to Wikipedia, it's a massive long list. But the first 3 are the ones that I'm particularly interested in: maintainability, testability, and deployability, because those are the attributes that directly impact your development velocity. Today we're all about sort of basically building and delivering better software faster. That's kind of the thing that we're focused on, right? And that's the motivation behind DevOps, Agile, continuous delivery, and so on. And that's becoming really important. There's the argument that businesses are needing to innovate faster. And what that means for us as developers is that, well, we have to deliver better software faster because we're creating the platforms that underpin the businesses, right? And in particular, we want to significantly reduce lead time, the amount of time between when we commit our change and when that change gets into production. Ties sort of very much in with the previous talk. And likewise, we want to significantly increase our deployment frequency. So if you think, I kind of think of software, sort of successful software development as requiring 3 things. One, you need continuous delivery, or sort of if you're operating some kind of SaaS or internal IT application, continuous deployment where you're constantly pushing changes into production. You want to organize around into small autonomous teams, because those are the teams that are sort of agile enough and can make decisions quickly and can have a practical stand-up every morning in order to get stuff done. And then there's the third component, which is architecture. And that's where this whole issue around monolithic versus microservice architecture comes into play. So, if we think about sort of the classic way that, we build applications, like pretty much every Java application that I've built over the years until relatively recently has had an architecture that's looked like this, where from a logical perspective, it's layered and it's modular, right? So this is an online store example. So there's the storefront UI that's a web application that's either generating HTML or exposing a REST API. Then the business tiers and data access tiers are comprised of modules that implement specific bits of business functionality, catalog, recommendations, reviews, orders, and so it would go on. So we have this wonderful logically modular and layered architecture. But then when it comes to actually deploy the application, we package it up as a single WAR file, or I suppose EAR file. And that's it. So we've sort of gone from this modular system into this sort of monolithic system. And that's actually, as I mentioned earlier, that this is the implementation view. We've got our implementation view consists of this single deployable or executable unit. And then there will be multiple instances of that from a process view perspective. So that's really the definition of the monolithic architecture, is an architectural style that structures the application from an implementation view perspective as a single executable component. And this is not a bad thing necessarily. If your application is small, it will have or should have good maintainability, testability, and deployability. It's not an anti-pattern to use a monolithic architecture. In the right situations, it works extremely well. The problem that you have is that if you build a successful application, it will keep growing over time, right? Unsuccessful applications just sort of die, right? And no one cares about them. But successful applications just grow. Every day the team of developers is adding more lines of code to the code base, and so it's getting bigger, and bigger. And if you're really successful, the development team grows as well. So sort of the rate of increase actually goes up as well because your team is getting bigger and bigger. And then maybe you're split into teams that are focused on particular functional areas, but your application is just sort of growing. So it's gone from this small, manageable monolith to a very large system. You can easily run into systems that are 500,000, million or more lines of code developed by quite a large team. And eventually you end up in a situation that I call monolithic hell, where any notion of agility, both from a development perspective and a deployment perspective, becomes extremely difficult. So basically, development just kind of crawls along. You can no longer practice sort of continuous delivery like we're used to, and the business gets unhappy with you. And then not only that, your application is usually ends up being built with a technology stack that is increasingly obsolete. But you can't change it because you've got this massive code base, and it's not practical to do that. So you end up in a situation where your abilities that impact your development velocity are poor. So you have poor maintainability, poor testability, and poor deployability. So you're in this unhappy place. You're not happy, business is not happy. And so that's where this microservice architecture comes into play. So it's an architectural style that structures the application from an implementation view perspective as a set of loosely coupled services. So a service is just a mini application. So a mini executable, a mini WAR file, executable jar, whatever you want. The key criteria is that they are loosely coupled for reasons I'll explain. And they're also organized around business capabilities. So each service is performing a particular business function. So if you think about what a business does, right? It's got, like in this online store, it does things like take orders, it manages inventory, it manages delivery, and so on. So those are your business capabilities. Those, this is a concept from business architecture. It's a little nebulous as to sort of pin down exactly what a business capability is, but business architects know what that is. So it's a way of modeling your business, and the idea is that you roughly map those business capabilities into a technical architecture comprised of services. So we'll have an order service, an inventory management service, a delivery management service, and so on. So you can sort of show your architecture at a service level to a business person, and it would relate to them. And it would be meaningful to them, which is actually kind of nice, because if you're on the team building a service, the business can appreciate the value of what you do because it's implementing a particular business function. So that's good. So one thing to note is, even though we call it the microservice architecture, which I think is a terrible name because the first thing you hear is micro, the actual size of the service is not kind of a primary goal. And in particular, you should not strive to have tiny services. I hear people, a few years ago, people were saying they should be 100 lines of code. Other people have said, maybe more recently, 2,000 lines of code or 2 weeks of code. To me, those guidelines are somewhat misleading, because the goal is to have a service for each service is for it to implement a meaningful slice of business functionality, one of these so-called business capabilities. It should be capable of being developed by a small team, this so-called 2-pizza team, though sort of appetites and pizzas vary in sizes, but like 6 to 8 people, once again, small agile team, and they should be able to do it with minimal lead time. So time from commit to deploy, with a high deployment frequency as well. And provided that you've satisfied those goals, it doesn't exactly matter how big your service is. I mean, some of them might actually be small. A team might own a collection of small services, but some of them can be quite substantial, provided it satisfies these requirements. This is the primary goal here. And this is sort of why, kind of then the other point, which is where the title of this talk comes from, is for me, when I say microservices, it's really just a shorthand for the phrase microservice architecture. Kind of works better in a sentence sometimes, which is a form of application architecture. And so for me, this is the reason why there's no such thing as a microservice. Right? So you only ever think of an application as being comprised of a set of services. And so you always have to have at least 2 for it to be meaningful. To me, this sort of helps kind of clarify the definition, especially when you hear someone will say, can I use a microservice for this? And it's like, well, not really. It's like a better question to ask is, can I structure my application using the microservice architecture? That's a much more correct usage. So, a lot of explanation, but the end result is when you architect your system using the microservice architecture, in particular this online store, you will end up with a set of services. So there will be a catalog service. That will be a web application with some kind of API. Likewise, a review service, order service, and so on. Potentially tens, maybe hundreds. Some people even have thousands of services. Like, I think Uber has more services than they do developers, which is slightly peculiar. So you have a set of services. Each service, if it has data, will have its own private encapsulated data store. Doesn't mean it has its own private database server, so you don't have to shock your DBAs by asking for an Oracle license for every single service. They can share databases. That's database servers. That's a capacity planning issue. But a key requirement is that the data that is owned by a service is private to that service, pretty much like the fields of a class. They're private and encapsulated. you can apply this functional decomposition to the web application as well. You can have different web applications handling different parts of the UI. Product search and browse, shopping cart, product detail page, and so on. And then you can have an API gateway that acts as a facade into the set of services so that collectively they can expose an API to clients, which could be third-party applications, could be mobile devices, or they could be JavaScript applications running in a browser. So, one thought is, golly, this is pretty complicated, right? Before we just had a bunch of tomcats that were load balanced, and look at all these moving parts that we have to set, kind of manage. And that's kind of a hint at the complexity, sort of one of the downsides of the microservice architecture. Oh, and I keep forgetting, yes, you can have a messaging gateway as well, because maybe suppliers are sending you catalog updates using some messaging-based infrastructure. So, that's kind of a quick overview of the microservice architecture. And the reason we're going to do this is, even though it's kind of, as a whole, there's a lot of complexity and a lot of moving parts, it actually gives us really good maintainability and testability and deployability. Because if you're a developer working on a team that owns a service, your universe really is that service. Yes, you're consuming the APIs of other services and you're exposing an API to other services, but your application is your service is going to be this relatively small body of code, which will be easy to maintain, easy to test, and also easy to deploy. So that's sort of the big motivation for using this microservice architecture. And to put it another way, it's if you want to do continuous delivery or continuous deployment, which is part of this whole DevOps phenomenon, if you're building a large, complex application, it's very likely that you will need to use the microservice architecture. And the reason for that is sort of twofold. So one, the microservice architecture gives you an architecture that's testable and deployable, which is a key requirement on the architecture in order to do continuous delivery deployment. Continuous delivery in particular relies very heavily on automated testing, so your software has to be testable. And large, complex monoliths usually are not testable in any sort of practical way. And then you also need the deployability, because you're potentially deploying into production many times a day. And it's usually not practical to do that with a large, complex, monolithic application, unless you try really, really hard. I mean, there are people who do that. And then also, this architecture enables the teams to be autonomous. The idea is that each team will own exclusively one or more services, which they can develop, test, deploy, and scale independently of the other services and the other teams. So that just lets them get on and do their own thing at maximal development velocity without having to be held up in tedious coordination meetings with other teams. And in particular, if you go back to the database, right? If I'm on a team and I need to change the database schema, if that schema is private to me, I can just change it. Whereas if there's 10 other teams who are accessing that schema, I'm going to have meetings with those 10 other teams, and the schema change is going to have to fit in with their schedule, which will slow me down and get in the way of continuous delivery and just be incredibly inefficient. Whoops. Oh, can I go back? Yes, there's a back key. So this is some absolutely fascinating numbers from the 2017 DevOps survey, where they sort of have some statistics showing the performance of kind of high-performing teams. So if you're on a high-performing IT organization, you're deploying into production many times a day. Amazon had a statistic. They were deploying every 11.6 seconds, which is mind-blowing. The lead time for changes from commit to deploy is less than an hour. Netflix had an example of 16 minutes for one service. And then they're moving fast, but not only that, they're also moving in a very safe way. So they're not breaking things. So they have a shorter time to recover from failures. And also their failure rate is much lower than sort of medium or low performing teams. Amazon had a statistic that where it was like 0.001% of their deployments actually caused an outage. So it's all about moving fast and not breaking things. And then also, the microservice architecture lets you evolve the technology stack. So when you're creating a new service, which is something you will do from time to time, you can pick a whole new technology stack. Or if you're making significant changes to an existing service, you can actually rewrite it. It's not going to be a hugely expensive multi-year effort to do that. And not only that, it lets you experiment with new technologies and sort of fail in a safe way. So for example, you might have heard that Golang is cool, right? Because Google uses it. And so you decide to implement a new service in Golang. And you succeed in building it, but then you realize that Golang is sort of a 1990s version of C. And you want to actually use a higher level language. Actually, one with exceptions as well. I just don't get the return code thing in Golang. But that's not a disaster. You've spent a relatively small amount of time successfully building a service that's in production using a technology stack that you have decided is not a good fit for your application. And it's just like, yeah, we learned something, right? We learned that we want to use a nice JVM-based language, right? And so next time we need to make any major changes to it, we're rewrite it. And that's really important. It lets you experiment and fail in a safe way. So there's some really, really awesome benefits of using the microservice architecture, but it really isn't a silver bullet. Fred Brooks, author of Mythical Man Month, said back in like 1985 that there's no silver bullet in software engineering. There's sort of no magical technology that makes everything perfect, right? There's no rainbows and unicorns. And certainly that's true. Well, it's true with every technology. There's always downsides to consider. And it's particularly true with the microservice architecture. And by far, the biggest drawback of using the microservices is complexity. You're now building a distributed system. So not only do you have complexity of development. Whereas before, if one module wanted to invoke another, that was just a simple method call. Now it's inter-process communication, with REST, gRPC, or messaging. So obviously there's libraries that help with that, but it's a bit more complicated. You have to deal with partial failure. The service you're trying to invoke might not be available. You need to program explicitly for that. Once again, there's a circuit breaker pattern and libraries to help with that. And then also the fact that each service has its own private data is a wonderful thing, but it's like, how on earth do you maintain data consistency, and how on earth do you do queries that involve joins across these across these services as well? And that is actually worthy of a whole other talk, because there's sort of a particular area of interest of mine, and that's sort of what my startup's doing as well. Event-driven architectures. Testing is, on the one hand, testing an individual service because it's small is relatively straightforward, but making sure that the services work together correctly is a challenge. But there are testing patterns for that as well, so that's good. And frameworks, like in particular, I just started using Spring Cloud Contract for testing service, for verifying that services properly work together. And then deployment is sort of complicated as well. On the one hand, yes, you can deploy a service, but on the other hand, there are now basically an order of magnitude or two orders of magnitude more applications in production. So from a sort of operational point of view, things are a bit more complicated. The nice thing is that there are automated deployment platforms. So it could be Docker orchestration frameworks like, Docker Swarm, Kubernetes. There are clouds that automate your deployments. There are PaaSes like Cloud Foundry that do it as well. So it's sort of like, yeah, there's all this extra complexity that you have to deal with, but on the other hand, there are solutions, or at least partial solutions to this complexity, whereas your monolith is just complex, and it's becoming more and more complex every day, and there's really no solution to that. So there is this, but to adopt the microservice architecture is not a trivial undertaking. So you have to ask, are microservices a good fit for my application? Do I have the prerequisites in place? Am I good at automated testing? This comes up a lot when I work with clients. It's like, hey, we want to use microservices. How's your testing? Well, we do it manually. You need to master automated testing, because that's sort of a critical foundation of modern software development. And if you want to go fast, you have to implement automated testing. Automated provisioning is also generally useful as well. I don't think it's quite as critical, but you should have that in place too. And then also, if you decide to use microservices, there's a whole bunch of issues that you have to address around decomposition, deployment, testing, observability, and so on. And so, your choice is whether to use it or not is somewhat, it really does depend on your particular situation. And so to help with that, I've created the microservice pattern language. I've been working on it for sort of two or 3 years now. So it's a collection of patterns that solve design and architecture problems around the microservice architecture. And it can help you make better decisions. So a pattern, of course, is a reusable solution to a problem that occurs in a particular context. And it was popularized by the Design Patterns book that came out in 1994, which is a collection of object-oriented design patterns. And patterns are actually really good because the format of a pattern encourages objectivity. So patterns obviously have a name. You have to describe the context, which is the situation within which you're trying to solve the problem, because a different situation might actually require a different solution. The pattern has the problem, of course, that you have to document the forces. So these are the issues that you have to address, and sometimes they're conflicting. There's the solution, that's the essence of the pattern, of course. But then there's the resulting context, and that has 3 subsections. You describe the benefits, which is usually what we all focus on when we talk about technology, or at least technology we like. It's awesome. And if it's technology we don't like, we just focus on the drawbacks, right? It sucks. But with the pattern format, you have to talk about both of them, benefits, drawbacks. And then not only that, you have to describe the issues that you then have to address if you've applied this pattern. Because it turns out when you pick a pattern, you have now created you've solved one problem, but you've created a set of hopefully smaller problems for yourself. So this format forces you to describe them. And then there's this section of related patterns, and those are patterns that are alternative ways of solving this very same problem. So the pattern points to its competitors, which is really useful. It says, well, you could use me, but maybe you should use that other pattern, like the monolithic architecture. And then there are related patterns that address the issues that this pattern creates for yourself. So it's a much better framework for thinking about technology. And so this is the pattern language. So if you go to microservices.io, you will see a much more readable form of this. There's some critical patterns here, right? The core patterns, monolithic versus microservice architecture. And then if you pick the microservice architecture, everything else solves problems within this architecture. So there are patterns around decomposition. How do I split my system up into services? There are patterns around managing distributed data. How on earth do I maintain data consistency and also do querying? And then there's sort of a bunch of technical patterns that are not quite as critical. And interestingly, those are the ones that people are mostly talking about today, like patterns around deployment, right? Cloud, Docker, yeah. But these are sort of less important than the first three patterns. There are a whole bunch of patterns around inter-process communication, because we're building a distributed system. And then there are patterns around observability, how, figuring out what on earth is going on inside my cluster of services as requests bounce around. So like distributed tracing and log aggregation are key patterns there. So that's pretty much my talk, which is good because I have just run out of time. So in summary, right, the goal of architecture is to satisfy non-functional requirements. And then when you want to do continuous delivery, you have to pick the appropriate kind of architecture. So if you're building a small system, the monolithic architecture is just fine, probably. If you're building a large, complex application, you should most likely use the microservice architecture. But once again, it really does depend on the specific situation. And then you can use the pattern language to help you decide, well, should I use the microservice architecture? Should I use the monolithic architecture? And then if you do decide to use the microservice architecture, how do I solve the plethora of design problems that I have now created for myself? So that's my talk. Thank you for listening, and I hope that you found this useful. And oh, shameless plug, discount code for my book. So thank you.